Hello everyone, welcome back to the MOOCs course on Advanced Analytical Technique. We are now discussing the second unit, Molecular Luminescence Spectroscopy. This is the fourth lecture of the sixth week that I am going to cover today. In the previous lecture, we have discussed about chemiluminescence phenomena, which is sometimes called as bioluminescence, and how we observe light from fireflies, from jellyfish and various other organisms, deep sea organisms, and how these chemiluminescence phenomena that are related to the chemical reaction which produces a more small amount of heat as an exothermic reaction causes the molecule to excite. Electrons are promoted to a higher level. When they come back, they releases light. So there is a chemical reaction which is the driving force for this visible light, and these chemiluminescence phenomena are very interesting. We also use it for the detection of blood and various other tests. So let us come to the application of molecular luminescence spectroscopy, especially the application of fluorescence spectroscopy. As we all know that fluorescence spectroscopy that is being conducted through a spectrofluorometer is used in the determination of fluorescence intensity from a molecule that is showing visible light upon absorption of light of shorter wavelength, and that light which is being emitted, if that light stops immediately after the incident light is cut off, this is called as fluorescence, and this involves singlet state only. Just doing a recap, electrons are excited from ground singlet to excited singlet, they go back, and when they come back they emit light radiation, and they are also excited by light radiation. Here we have higher energy, shorter wavelength, here we have lower energy and longer wavelength. On the other hand, in some cases, electrons from excited singlet undergo flipping, where the spin changes from paired spin to parallel spin. They comes to triplet state, and when they come back, they again emit light. Since triplet state is involved, the light being emitted continues for a longer period, even up to 100 seconds after the incident light is stopped, and this is called as phosphorescence. Both these fluorescence and phosphorescence phenomena comes under the category of molecular luminescence, and both are quite specific. Phosphorescence is even more specific than fluorescence. But fluorescence is widely used in chemical analysis, in biological samples, in the medical sciences, and as well as in the environmental monitoring. Although it is sensitive, but still there are certain approaches that can be used even for compounds that are non-fluorescent, which we have already discussed. The direct method that are used to study the fluorescence properties of naturally fluorescent compound. Then there are indirect methods that can be applied to molecules that do not flourish. So in this way we are broadening the application area, we are broadening the domain of these fluorescence methods. And in those methods, one is called as indirect or the derivatization method, in which we have fluorescent tags or we attach fluorescent dyes, and in the second method we add called as quenching method. So in those method, while doing the analysis, a fluorescent molecule is added and our non-fluorescent analyte attaches to it, and in this way quenching happens, and based on the reduction in intensity we can identify the presence of the analyte, and if it is present we can also identify its concentration based upon the decrease in the intensity of fluorescent radiation. And therefore these two indirect methods made this technique a widely used technique in research and innovation. It is widely used for quantitative determination as well. It is also used for qualitative analysis. Because of its high sensitivity, it is very sensitive as well. Even small traces of a sample can be detected, can be identified, and at the same time it is selective as well. For example, we have 20 molecules in a sample. While only one is showing fluorescence, we can identify that one compound very easily. But if on the other hand we are using absorption method, since all 20 molecules absorbs at one or the other wavelength, we'll get numerous peaks, making the spectrum very complicated, and we cannot identify that compound easily. But with fluorescence methods, we can identify it very easily. Even a compound which do not flourish, we can make it flourish according to our needs. That is the beauty of fluorescence methods. The intensity of the fluorescence light that is being emitted in the visible region is proportional to the concentration of an light under study. So we can do quantitative as well as qualitative analysis. So we can do quantitative as well as qualitative analysis. Now, these methods can be applied to organic as well as inorganic molecules. So, like the previous unit, which is mainly devoted to elemental analysis, the atomic absorption and atomic emission technique can help you to identify heavy metals. Mainly it is devoted to metals, although some metallites can be analyzed. Even with AES using ICP, we can go for refractory metals which have very high melting point. We can analyze lanthanides and few actinides as well. Even in some cases, we can identify some non-metals like carbon, nitrogen, oxygen, sulfur. Although there may be some reliability issues with these results, but we can go up to some non-metals. But with those techniques, we can only identify whether carbon is there or not, whether sodium, potassium, copper and Al is there or not. We cannot identify the nature of the whole compound. For example, we have a compound tetraethyl lead, but the fluorescent methods can be used for organic molecules as well as inorganic ones. Many of the organic molecules, especially the aromatic compounds, are fluorescent. So we can identify these aromatic compounds directly. And those organic molecules which do not flourish, even biological molecules like proteins, biomolecules, if they do not flourish, we can go for a derivatization method. But for organic molecules, especially the aromatics like naphthalene, anthracene, they are fluorescent, we can easily identify them. Similarly, polycyclic compounds can also be identified where we have more than one cyclic structures. Even drugs or pesticides can also be identified with these techniques. Quinine, riboflavin, vitamins, vitamin B1 can be analyzed, B2, B3, A, retinol, they all can be identified by fluorescence methods. So, biomolecules can be identified, drugs can be identified. Then comes the derivatization reaction. Even as I said earlier, even the non-fluorescent compounds can be converted into fluorescent ones and identified and studied. For example, this table shows a number of target analytes that can be analyzed by fluorescent methods. Now in this table, some of the compounds that are naturally fluorescent does not require any derivatization. For example, the first one, quinine. For example, the quinine molecule can be identified, and since it is a naturally fluorescent compound, we do not need a derivatizer for it. It undergo when it is being illuminated with light, it absorbs light radiation of 330 to 50 nanometers, while it emits light radiation at 440 to 460, means the light of shorter wavelength at high energy is absorbed. Some of the light radiation is lost during vibrational relaxations or internal conversion, which are both types of non-radiative energy loss and non-radiative deactivation, while the remaining energy of the electrons when they comes to the ground state, it is being emitted at 440 to 460 nanometer. And you can check the sensitivity of this technique, ranges from 0.0001 milligram per liter. Milligram per liter already means ppm, and 0.001 milligram means 0.1 microgram per liter, which can be converted into 0.1 ppb level. Look at the sensitivity of this technique. Although there are certain interferences as well. The ionic strength, if the strength is too high, of course high concentration of quinine will affect the results. Although of course high concentration of quinine affects the results. Some alkaloids may also cause interference. there is a possibility of inner filter effect. Do you know what is inner filter effect? When the light that is being excited, when the light that is absorbed for excitation, which causes then emission, the emitted light is absorbed by the same molecule. That is called as inner filter effect or internal quenching. And the same molecule that has been excited upon absorption of light, when it emits light, it again absorbs that light radiation. That is called as inner filter effect. Due to that also we have interference. Again, we have a molecule tryptophan. It is a protein. We do not require any derivatizing agent, and we can easily, and they show absorption at shorter wavelength with higher energy radiation, while they emit light at longer wavelength, the colorful light in different colors ranging from violet, indigo, blue, or maybe red. And look at the sensitivity of this technique. Here you can see 0.1 to 1 microgram per ml. Here you can see 0.001 milligram, means 1 microgram per ml. Look at the sensitivity of these techniques. Of course, there are certain interferences, but we can avoid these interferences. This is the beauty of fluorescence technique. In some cases, we need compounds that causes, even we can analyze those compounds that causes derivatization. Some compounds, while in this case no derivatizing agent are needed, but for some we can convert them and derivatize them from non-fluorescent to fluorescent compounds. Then this table shows few examples like aromatic amines. They do not fluoresce, but we can make them fluoresce through derivatization, and the derivatizing agent for these aromatic amine is the fluorescamine or densyl chloride. When we add these densyl chlorides, they convert these non-fluorescent aromatic amines into their fluorescent derivatives, and these derivatized molecule absorb light radiation in the region 350 to 380 nanometers, while upon excitation, when the electrons return back, they emit light of longer wavelength, means their peaks are like this. We have a clear distinction between these two peaks, which is called as Stokes shift. And still these derivatization methods are highly sensitive. We can go up to very low concentrations, means this is again 0.5 to 5 microgram per ml. So in some cases we have incomplete derivatization, or we have primary and secondary amines as well. And even if the derivatization is complete, we have to remove the derivatizing agent, because since it is a fluorescent compound, if it is still present outside the complex, means it is still present in pure form, it will also give its fluorescent signal, and the complex will also give its fluorescent signal, but which will create complication. And therefore we add a small amount of derivatizing agent, just sufficient to derivatize the molecule, and then we try to separate or remove the excess derivatizing agent, so that it will not give its own fluorescent signal. And when it is removed, we have only the derivatized analyte, and now the signal of the fluorescence or the fluorescence light or the fluorescent light that is obtained belongs to the derivatized sample, whose concentration is directly proportional to the intensity of light emitted. So next example is phenols. Even trace phenols can be analyzed by fluorescence spectroscopy, although they are not fluorescent, or I should say non-fluorescent compounds. We can add densyl chloride or NBDCl. Derivatization, they are derivatized to form fluorescent derivatives which absorb light from 320 to 360 nanometer. Again, emit light from 450 till they can go up to 520 nanometers. The sensitivity is also good, although it depends upon the pH variations, but we can control that, and in this way we can study phenols. Then we have carbaryl, which is already a fluorescent compound, so no derivatization is needed. Porphyrins, even chlorophyll, the green pigment of plant, since it is a fluorescent compound, it can be detected. And humic or fulvic substances or humic acid, that is a mixture of different acids of with large molecules. They are fluorescent compounds, and therefore they do not require any derivatizing agent, and these humic acids are weak acids, and they can be analyzed with spectrophlorometers. Although there are some broadening of signal and pH effects, sometimes metal complexation, but we can minimize these with careful sample preparation and experimental analysis. And this way we can detect a large range of organic molecules that belongs to fluorescent and non-fluorescent systems through fluorescence. Then we'll move to the inorganic ions, which can be studied by fluorescence. Some of those inorganic ions fluoresce, like europium, like we have like we have cerium, but most of them which do not fluoresce, that can be detected through quenching. Then even inorganic species can be identified. These inorganic species can be identified in two ways. First is first are those inorganic species that are fluorescent. We can go for certain lanthanides. We can identify cerium plus 4 state. We can go for copper. We can go for europium. They can be identified because of their fluorescent nature. But most of the inorganic ions are non-fluorescent, and by using the method of quenching or fluorescence quenching, we can identify those compounds. For example, we have a sample in which we have some reports that this water that is coming from a river or coming from groundwater has some heavy metals present in it. Now, if heavy metals are there, they form complex with fluorescent compounds, leading to quenching, reduction in the PL intensity or the photoluminescence intensity of those fluorescent compounds. Now, what do we do is we take the fluorescent compound in pure form, do the fluorescence intensity test using spectrophlorometer and note down the fluorescence intensity. And then we add the same fluorescent molecule in this particular sample, or we add the sample water from this sample into this into this solution of a fluorescent molecule which is already showing fluorescence. Now, the moment we add this sample, and if it contains some heavy metals, those heavy metals immediately go and bound to these fluorescent molecules. The moment it happens, there will be marked shift or significant decrease in the fluorescence intensity, and at that particular point we can say that yes, of course, some heavy metals are present, and then based on the reduction in the intensity of fluorescence radiation, we can even identify the concentration of those heavy metals. Clear? Although in all these tests we have to we have to keep some controls over the reaction conditions. For example, when the complex is formed between these inorganic ions, these heavy metals and the fluorescent molecules, we have to maintain the pH, ionic strength, as well as the temperature under control. We have to maintain all these parameters at their optimum level for that particular reaction. Look at these inorganic species. Aline, which is a non-fluorescent, aline, Al plus 3, which is a non-fluorescent molecule. It can be easily detected by alizarin garnet R because it is a fluorescent molecule. When it is irradiated with UV visible light, it absorbs light radiation at 470 nanometer in the visible region, but it emits light at 500 at even longer wavelength. Means here we have lower wavelength and high energy, but when it emits light radiation, a light radiation of longer wavelength and lower energy, the sensitivity is also good. So in this way we can identify Al plus 3 because it reacts with alizarin. However, this alizarin can also react with these metals, so there may be some interferences, but not all these metals are present all the time in Al. If we have Al only in a sample, we can easily identify its concentration, we can easily determine its concentration, and if these metals are present, we can remove them by some other method, or at least if they are present, we can have an idea whether Al is present or not, because if the intensity goes down, we still have some reliable result that yes, of course, intensity is going down, there is a possibility of Al. We can then do further analysis to confirm our doubt, to clear our doubt. Similarly, even fluorine F negative, it is not metal, it is a non-metal, even it can be detected. The Al complex of alizarin means in this case when Al forms complex with alizarin, quenching occurs. If F negative is present, we can have quenching, and we can also identify the anion. And as you all know that hardness in water is because of the presence of cations, and those cations which have plus 2 plus 3 and plus 4 charge means hardness is not caused by Na plus K plus, but hardness is caused by Ca2 plus Mg2 plus iron plus 2 plus 3 both and all metal ions. Now in order to check the hardness we can add alizarin dye. If intensity is decreasing, we can say that yes, of course, metal ions are present. Similarly, cadmium, lithium, tin, zinc, they can be identified using different molecules like benzoin, flavanol, hydroxyphenyl benzoxazole can be used for cadmium. For borate, we can use benzoin again. It absorbs light for excitation at 370 while emit light at 450, and there are very little interferences as well, only beryllium and antimony. Similarly, in case of cadmium, there is only possibility of ammonia. We can easily remove ammonia. It's not present everywhere, just like oxygen. So we can identify this cadmium just by adding orthohydroxyphenyl benzoxazole. It absorbs light for excitation at 360 while emit blue light in the starting visible region, giving blue color. These are those molecules 8-hydroxyquinoline, that is this is used for the analysis of lithium by quenching methods. Flavanol, this is used for tin. So this is used for lithium. This is used for tin. Similarly, alizarin garnet are used for Al3 plus, even for F negative. Benzoin used for Zn, even for borate. So in this way, these fluorescent molecules can be added to these respective metal ions or even an anion. Quenching happens and we can identify through the method of fluorescence or fluorescence quenching. Of course, these fluorescence methods have several limitations, means the PL methods, photoluminescence methods, for studying molecules of both organic and inorganic origin for their quantitative as well as qualitative analysis. Of course, there are certain limitations to these fluorescence methods as well. First of all, the quenching effects. The fluorescence intensity may decrease, as we all know, due to impurities, heavy metals, or molecular collision. So when we are using quenching methods, we are basically adding fluorescent compounds so that those metal ions or those organic molecules that do not fluoresce, they come and make complex with these fluorescent molecules, resulting into quenching, the decrease in fluorescence intensity, so that we can say that yes, that particular compound is present. But this complex between the fluorescence molecule but this complex between the fluorescent molecule and the analyte, whether it is organic molecule or an inorganic ion, this is not the only reason for quenching. That quenching may occur due to an impurity, due to some other heavy metals, or sometimes due to molecular collisions, because molecules in a liquid are moving even if the temperature is low, although at that low temperature the speed is low. Even then these phenomena is taking place, and molecular collision also causes quenching. So if we it is very difficult to differentiate between it is very difficult to differentiate that whether the quenching is caused by the complex formation between analyte and fluorescent molecule, or it is being caused by the impurity or by molecular collision itself. Even at lower temperature also there are molecular collisions. Of course, at high temperature they are very uh, there are high energy collisions. Specifically for phosphorescence studies, we need very low temperature because we want to avoid all these collisions. Then only light will be emitted for a longer period of time. Then the self-absorption or inner filter effect. This is because of very high concentration of the sample. Sometimes when the light emitted, it is being absorbed by the excited molecule, when it comes back emitting light and comes back to ground state, it absorbs, or sometimes this light is being absorbed by other molecules. So that also causes some ambiguity in the study. Then interferences from the matrix components, means the matrix, basically the sample. For example, if you are working on a blood sample, the various components of the blood, the plasma, the RBC, or even the protein that is present as a clotting agent, that may also interact and interfere. Similarly, if a soil sample, if you want to study some metal ions by fluorometry, even after extraction of metal and filtering the sample to avoid components of soil, still we have some interferences. River water, it may contain various mixed impurities that may interfere with our compounds, that may show fluorescence, although we do not want them to fluoresce. They show some light, or sometimes if they are not showing, they absorb light of the fluorescent compound, causing quenching. So it makes the analysis a bit ambiguous. So it makes the analysis a big so it makes the analysis a bit ambiguous, a bit confusing. Then there is a possibility of photodecomposition. For example, then there is a possibility of photodecomposition. That's all. That's another limitation. For if we are irradiating a sample for a longer period of time with a UV light or light from the visible region, upon prolonged exposure, the molecule decompose, and if when the molecule does not exist, how we can identify it? So it happens because of prolonged exposure of the molecule with the light that is being used for irradiation to cause excitation, that because that is a high energy radiation while the light emitted is low energy radiation. So when this high energy radiation being used for irradiation for a longer period of time, it causes decomposition of the compound. So it damages the compound. The total study is gone, means the total efforts are in vain. Then these fluorescence methods are dependent greatly on the pH as well as the solvent sensitivity. They are very sensitive to solvents. If a compound is fluorescent in one solvent, it may not be showing the same phenomena in the other solvent. Even they are quite delicate to the changes in pH. Just by changing, sometimes we have dyes that show color or that show fluorescence phenomena at high pH, while sometimes at low pH. And I told you when I was explaining you the factors, I told you that although pH has a complicated effect, sometimes low pH favors while sometimes higher pH, but most of the time we can say that higher pH is a bit optimal for fluorescence, because at lower pH acidic content is high and we have H ions in the solution. And if for example we have a molecule that is an aromatic ring showing the phenomena of fluorescence there because of the N2 pi star transitions, H ions, hydrogen ions, they go and attach to this moiety because of the electron rich center. This lone pair is not available for N2 pi star transition, and therefore no fluorescence happen. That's why low pH or changes in pH are not favorable for fluorescence studies. Similarly, temperature effects. High temperature, I told you in the factors that high temperature causes more molecular collisions. These molecular collisions result in the loss of energy. They causes quenching. So there will be no light radiation even between the molecule of the same sample, because they are now colliding with high kinetic energy because of the high temperature. Similarly, the viscosity of the solvent. If the solvent is less viscous, these molecules can move and they collide each other with high energy, resulting into quenching. While if the solvent viscosity is little bit high, the molecules cannot move. If they move slowly, and therefore the collision does not happen. And if the collision, then therefore the collisions do not happen. And if they happen, and even if they happen, they are not with enough energy to cause quenching. In summary, we can say that still we have large but still we have wide usage of these fluorescence methods, although there are certain limitations, but still we use them on a wider scale, and they are quite sensitive, provides reliable data and reproducible data. So in summary, I can say that fluorometric methods offer excellent sensitivity. They are very sensitive, and specificity, because they can naturally they can because normally they can be applied to naturally fluorescent compounds only, because compounds that do not fluoresce cannot be studied. So in normal case, if we want to study the fluorescent compounds only, so these methods are very sensitive. But in case we want to study more compounds, we can easily make them fluoresce. Then, however, experimental control for these methods is critical, because we have some interference in the form of impurities, some interference in the form of molecular collisions, or they are sensitive to temperature and effect, or they are sensitive to temperature and pH effects, or maybe the solvent viscosity. Still the results are reliable, and we can, because we can control these parameters, and we can have reproducible results. Still we can control these parameters, and we can have reliable as well as reproducible results just by doing proper sample preparation, making proper calibration curve with utmost care, and optimizing the instrument. We of course reduce all these interferences to get reliable results. If we are committed to perform study with utmost care, and we are very vigilant during the sample preparation, just by doing sample preparation properly, doing proper calibration and instrumental optimization, we can control these interferences of pH, temperature and solvent viscosity, as well as the molecular collisions and impurities, and then we can have very reliable and reproducible results. So with this, we have completed the molecular luminescence spectroscopy, and I hope you have learned about the concept of fluorescence, phosphorescence, chemiluminescence, as well as the factors that affecting the phenomena of molecular luminescence, and what are the main components of molecular luminescence spectroscopy, like the light source, monochromators, detectors, output device, and what is happening, and how we measure these, how we measure the concentration of these samples, as well as their qualitative studies by doing direct fluorescence measurement, by doing direct fluorescent measurements, or by derivatization, or through quenching. With this, I hope that you have understood the concept of molecular luminescence, and you like these videos, and they are very useful for your studies. Take care. Thank you very much.